Hello dear students. So in my last class, I started discussing about thermoanalytical methods. So there I explained about introduction to thermal methods of analysis, what is meant by thermal methods of analysis, and I explained about thermogravimetric analysis, what is meant by thermogravimetric analysis, and what is the principle involved in thermogravimetric analysis. And we took an example of silver nitrate AgNO3, and we saw the thermal analysis of silver nitrate. There we saw at what temperature does the decomposition of silver nitrate is going to take place, and till what temperature, that is 608 degrees centigrade. So till 608 degrees centigrade, so the loss in mass is going to continue and the mass of the sample remains constant beyond this temperature. So this was discussed, and also we saw about the instrumentation, what and all the components are there in the thermogravimetric analysis instrument, that is the balance, furnace temperature programmer or controller, and recorder. So these are the main different components which we saw in thermogravimetric analysis instrument. And also we saw a number of applications where we are going to use the thermogravimetric analysis technique in various analysis, which includes the organic chemistry, inorganic, and also mainly the analytical chemistry. Analytical applications were widely using the thermogravimetric analysis technique. And also we discussed about derivative thermogravimetry, so where we have very close change in the weight is observed. Okay, so the derivative thermogravimetry is useful for complicated decompositions where weight change occur at close temperatures. We saw how the thermogram looks like, and we took an example of copper sulfate, right? So how the decomposition of copper sulfate is going to take place, and we saw the thermogram was showing 6 peaks, which was indicating that there are 6 decomposition steps when a copper sulfate pentahydrate is heated. Okay, so this is where we stopped in our previous class, and in this session, so let us begin with the differential thermal analysis. Okay, so this is another thermal methods of analysis which is more popular thermal analysis or thermoanalytical technique, and is often used to measure the temperature of a material, which in turn is used to measure the endothermic and exothermic phase transitions of a material. Okay, so differential thermal analysis is a popular thermal analysis, thermoanalytical technique, which is used to measure the temperature of a material. So in this technique, it has found a lot of use across the pharmaceutical, organic, chemical, inorganic materials, food, cement, mineralogical, and archaeological sectors. So in all these sectors like pharmaceutical area, organic chemistry research, inorganic materials research, and food industry also, and in cement, and in mineralogical and archaeological sectors. So these are the various different sectors where the differential thermal analysis technique has found a lot of uses. Okay, now we will see what is meant by differential thermal analysis. So it is a technique, it is a method of analysis in which one is going to examine the heat effects. Okay, so the heat effects are going to be examined in differential thermal analysis. So it is associated with chemical and physical changes of a substance are recorded when it is heated at a linear rate. So here the substance which is under examination, so it is going to be heated at a linear rate. So here the increase in the temperature will be in a linear rate. A linear rate means there should be a difference specific difference between the rise in the temperature. Okay, so while increasing the heat to the substance at a linear rate, so we are going to examine what and all the chemical and physical changes are going to happen to that substance. Thus, differential thermal analysis is defined as a technique in which the temperature difference between the sample and thermally inert substance is continuously recorded as a function of furnace temperature or time. Okay, so this is how we are going to define differential thermal analysis. So in this technique, so we are going to heat up the substance continuously, okay, recorded the changes what and all is going to take place, whether the physical change or a chemical change is going to be recorded continuously as a function of furnace temperature or time. Okay, so this is a typical representation of differential thermal analysis graph. Okay, so this is called as DTA graph. So here we are going to plot this graph as a delta T, that is a change in temperature versus the furnace temperature T. Okay, so this curve is called as DTA curve. Okay, so here, so this is what is called as change in temperature. So beyond this or below this is endothermic reaction, and above this is defined or understood as a exothermic reaction, and this the central line is called as baseline. Okay, so the DTA curve, that is the differential thermogram, consists of a record of differences in sample and reference temperature, that is delta T versus furnace temperature. The shape and size of the peaks furnish good information about the nature of the test sample. Okay, so here how the curve is observed. Okay, so how we are going to see the shape and size of the curve or the peaks, depending upon that we can get a good information about the nature of the test sample. Generally, sharp endotherm peaks gives us the idea of change in crystallinity or fusion process. Okay, so this is a sharp endothermic peak. So this sharp endothermic peak gives us the information about the changes in the crystallinity. Say for example, if we are using an inorganic salt or an inorganic compound which is in a crystalline state while starting the reaction, so the crystalline state is going to get converted into a amorphous or a gaseous state. Okay, so this sharp endotherm peak gives us the information that there is a change in the crystallinity or fusion process, whereas the broad endotherm peak signifies that, suppose if this peak is very broad means if we have a peak like this, if we have a broad peak, then it signifies that dehydration reaction has been taken place. Okay, in most of the cases physical changes give rise to endothermic curves, whereas chemical reactions, particularly oxidation, gives rise to exothermic peaks. Okay, so oxidation reaction is a reaction where we will observe exothermic reaction. Okay, so the exothermic reaction, so this is the peak which represents the exothermic reaction. So this exothermic peak is observed means so it signifies that there is a chemical reaction has been taken place and it might be oxidation, whereas the endothermic curve, this gives us the information or it signifies the physical changes which has been taken in the substance which is under examination. Okay, so the difference in temperature delta T, always delta T means difference in temperature. It depends on the difference in energy between the products and reactants or between the two phases of a substance. Okay, so the two phases of a substance means always we understand in a chemistry language that when a product is formed, so definitely there should be a reactants. Okay, so when the two reactants react with each other, say for example A plus B gives rise to C means so here A and B are called as reactants and C is called as products. Okay, so here the difference in temperature is defined, or it depends upon the difference in energy between the products and the reactants, or between the two phases of a substance. Okay, so this is what the principle of differential thermal analysis is going to explain about. And next, moving on to the instrumentation part. So the various components of DTA apparatus are, so mainly we should have a furnace. Okay, so furnace is a device which is used for the heating of the sample, which contains a sample holder and reference holder. Okay, so now we will see where do we find furnace here. Okay, so this will be called as a furnace. Okay, so in this block diagram, so this is the block diagram of instrumentation of differential thermal analysis, and this will be the furnace. So this furnace will be controlled, or it will be connected to a furnace controller. We should have a furnace controller because, so the principle of differential thermal analysis is that, so here we are going to heat up the substance at a linear rate of increase in the temperature. To give a linear rate of increase in the temperature, definitely we should have a furnace controller. Okay, so along with that we should have a reference furnace. Okay, because here the graph in the thermogram, in the DTA curve, we are going to plot the curve against change in temperature versus the furnace temperature. So that is why, so our reference should be there. Okay, so both this reference furnace and a furnace controller will be connected to the furnace. Okay, so furnace is a device which is used for the heating the sample, which contains a sample holder and a reference holder. Okay, and the next component of DTA is a DC amplifier. So generally a low level DC amplifier is employed. Okay, so you know why do we use amplifier? So to pass the current to the furnace, so we have to control the temperature here, or the heat has to be controlled here. So for that purpose we are going to use a DC amplifier. Generally we are going to use a low level DC amplifier in DTA apparatus. Okay, and the next third component is a differential temperature detector. Okay, so differential temperature detector also is one of the important component of differential thermal analysis. So the function of this detector is to measure the differential temperature. So this differential temperature detector is going to measure the difference in the temperature, that is delta T is given by the differential temperature detector. And the fourth component is a furnace temperature programmer. Okay, so furnace temperature programmer is mainly used, or the main function of this is to increase the temperature of the furnace as a steady rate. Okay, so this is what is needed in a DTA. That is, we have to increase the temperature of the furnace at a steady rate. We should not increase it at once, or the temperature should not decrease at once. The increase or decrease in the temperature should be controlled, and it should be at a steady rate. For that purpose we are going to use furnace temperature programmer. Okay, so this is all what is going to take place during the differential thermal analysis. And the next important component is a recorder, and what physical and chemical changes that has been taken place in the DTA apparatus that has to be recorded. For that purpose we are going to use a recorder, and this is to record the DTA curve. And the last component of differential thermal analysis is a control equipment, and its function is to maintain a suitable atmosphere in the furnace and the sample. Okay, so this, as the name itself says, control equipment, means it is going to control the suitable atmosphere in the furnace and the sample. Okay, so this is how we are going to explain the instrumentation of differential thermal analysis. Okay, so mainly there are 6 various different components of DTA apparatus, and they are: the one is furnace and DC amplifier, differential temperature detector, and the fourth one is furnace temperature programmer, and the fifth one is recorder, and the sixth one is control equipment. And okay, so this is very important questions from the exam point of view. Then explain the instrumentation of differential thermal analysis. Then you have to write the block diagram. Okay, so this is the block diagram of differential thermal analysis, and you have to explain each components in 1 or 2 sentences. Okay, what is meant by furnace, what is meant by DC amplifier, and what is the function of it. So if you explain it in 1 or 2 sentences, that is more than enough. So you have to concentrate on the instrumentation part of differential thermal analysis. Okay, and next, moving on to the difference between the curve of thermogrametry, differential thermal analysis, and DTG, that is derivative thermogrametric analysis. Okay, so let us take this figure, that is figure A. So this figure A represents the thermogram of thermogrametric analysis. Okay, so what is observed by looking at the thermogram of TGA, that is thermogrametric analysis? What and all the informations we are going to get is, so mainly what happens in a thermogrametric analysis. So in this the weight of a sample is recorded as a function of temperature. Okay, so we are going to measure the weight of a sample in TG, thermogrametric analysis. So here the horizontal portion, that is plateaus, so this one, the horizontal portion indicate the region where there is no mass change. Okay, so this is the horizontal plateaus or horizontal portions. So this horizontal portions says that there is no change in mass. So this shows about thermal stability of the material. What does it mean? So here if you see the arrow mark, so here the increase in temperature is going to take place, and here in y-axis, so the decrease in mass is going to take place. So here if we have a horizontal portion, means it means that, so till this temperature, suppose if this is 100 degree centigrade and this is 500 degree centigrade, the substance or the sample is thermally stable up to 500 degree centigrade. Okay, so this is what is understood from this horizontal portion. And again coming to here, suppose if this is 700 or 750 degree centigrade, so from here again the compound or the sample will have thermal stability. Okay, so the curved portion, so this is the curved portion, that is B to C. So this curved position indicate mass loss. Okay, so this is what is understood by looking at the thermogram of TGA. Whereas the derivative thermogrametric analysis, so this is figure B. Figure B is the representation of derivative thermogrametric analysis. So here the rate of change of mass, that is dW divided by dt, is plotted against temperature. Okay, so this is temperature and the rate of change of mass. So here not only the mass is measured, but the rate of change of mass is measured. That is because, so where do we use derivative thermogrametry? So we are going to use it for the samples or the substances which have a weight change which occurs at close temperature. Okay, when weight change occurs at close temperature, it complicates the decomposition. We cannot find out the exact change in mass. So for that reason the derivative thermogrametry is used to record the rate of change of mass, that is dW divided by dt, which is plotted against a temperature T. Okay, so the derivative curve may reveal information that is not detectable in an ordinary thermogram. Okay, so this is what is understood by looking at derivative thermogrametric thermogram. And in the last method, that is DTA. So this figure C shows DTA thermogram. So as I have explained just now, so in this the peaks appealing above 0, let me take this as 0. So this is in y-axis I am going to take the change in temperature, and in x-axis the furnace temperature is recorded. Okay, so here the peaks appealing above 0 on the coordinate scale are the consequences of exothermic process, whereas those peaks below 0 corresponds to the endothermic process. Okay, so this is the differences between the three thermal methods of analysis which we have studied in this chapter. That is, in thermogravimetry, so we are going to measure the weight of the sample. Okay, so this is how the thermogravimetric thermogram looks like. Okay, so we are going to measure the weight here, and in DTG, that is derivative thermogravimetry, we are going to measure, or we are going to examine the rate of change in mass which is plotted against the temperature, whereas in DTA, so we are going to examine whether the changes taken place are exothermic or endothermic. By looking at that, we can make out whether physical changes has been taken place or the chemical reaction has been taken place. So all these things can be understood by looking at the thermogram of DTA analysis or DTA curve. Okay, so to conclude differential thermal analysis, so differential thermal analysis is formally defined as a method of determining the temperature difference between the sample and the reference materials. Okay, so here we are going to use a reference material, and that reference material is also heated at a linear rate. In practice, it can tell the user a lot about the phase properties. Okay, so the phase properties are the physical changes, physical properties which are going to take place. That is the change of a sample from the crystalline to the amorphous or a gaseous state, or a fusion reaction which is going to take place. So all these phase properties can be easily studied with the help of differential thermal analysis. Okay, and so the amount of information which is obtained through this differential thermal analysis will be of a great benefit to many industries. So this is why, hence, due to all these reasons, so it is widespread in use. Okay, so DTA is also widespread. It is widely applicable in various industries. As I have told in the beginning of this class, we are going to use this technique in various different fields, like we will use it in pharmaceutical industries, pharmaceutical area, organic and chemical research fields, and also inorganic materials. For the characterization of inorganic materials, we are going to use differential thermal analysis techniques, and also in food industries we will use differential thermal analysis, and in inorganic or industries like cement manufacturers, we are going to use this technique, and mineralogical and archaeological sectors. So these are the various different fields where the applications of differential thermal analysis is seen. Okay, so this completes this chapter, and I hope you didn't find any complications in this chapter, because it is completely of a theoretical part, and also some graphs are there which are clear, which can be clearly interpreted and clearly understood. Okay, and from the exam point of view, you can score more marks if you concentrate on these thermoanalytical methods, and also the flame photometry which we discussed in the last week's classes. So flame photometry and thermoanalytical methods, so these two are very easiest chapters in this fifth semester syllabus. So concentrate on this, and definitely you can get up to 15 to 20 marks questions will be asked in the examinations from these two chapters. Okay, so this completes thermoanalytical methods, that is chapter 2.3, and I have not yet decided which chapter has to be started in my next class. Hopefully I will see that I can, if it is possible, I will start up with the electronic spectra of transition metal complexes, that is chapter 2.1 in this same unit 2 in paper 6. I may start with the electronic spectra of transition metal complex, or we will start with the quantum mechanics. So another interesting topic is there, so that is in paper 5, I think. I'm not sure. I think in paper 5, no, not in paper 5, so that is in uh, paper 6, unit 1, that is elementary quantum mechanics. So that is also a very interesting topic, since you are already studying the dual nature of matter in physics. So the same thing is dual nature of light is going to be studied in elementary quantum mechanics. There is a lot of similarities between the topics which you are studying in physics and also the topic which we are going to study in quantum mechanics in our part of syllabus. So we will see which to start, and if you have any suggestions, if you want to start up with any of the topics, if you have any suggestions, you are free to call me and ask me to start with either quantum mechanics, or if you want electronic spectra, so that also so you can suggest me. And if you have any doubts in this regard, so I request you, please be open. You are free to ask any doubts if you are having, and we will have an open discussion in Google Meet session also. So I am going to stop it here, and in my next class we will start with the new unit. Okay, so I thank you, dear friends.